All right. Thank you so much. Thank you so much for having me here. I'm very excited. My first time in Japan, and I've been super impressed by the conference. I attended the demo session yesterday, and this is fantastic stuff. I hope to see more of this work actually also made available to people in other conferences. Please submit to Wiss and Kai. Hope to see you there. All right. So when I left Microsoft 7 years ago, and joined as a faculty member at Hasso-Plattner Institute, we started working on interactive systems and a lot of prototypes. So here's a system we published at WIST a year ago called Fabrication, a touch screen that actually recognizes users by their fingerprints across the entire touch surface. And here's another example of something we worked on. We built very large interactive systems. Here's a system called Gravity Space. A touch floor of 13 megapixels, input and output, that recognizes users by their shoe prints and reconstructs their body posture just based on the sensing system. So we had a really good time working on these systems, and the last keynotes I gave were all about natural user interfaces. So that said, I stopped doing all this because I've got something new that I really fell in love with, and I'm here today. This is the first time I'm giving this talk, so I hope you're going to material and including the fact that I just took on 3 new students, one with an electrical engineering background, one with a mechanical background, and one with a mechatronic background, reinforcing the team of computer scientists. And the topic I want to talk about today is fabrication. So here's just as a preview, here's one of today. This is a system called Wireprint, and it's one of many prototypes we built so far, allowing you to fabricate things very, very quickly. All right, so let's talk about personal fabrication. So there's not much I need to tell you. I mean, I know many of you are familiar with the topic, and then there also was a booth here at the conference from one of the key manufacturers showing like products made with the Object 500 3D printer. So I know many of you checked this out, and I know how many of you actually have a 3D printer at the lab? Okay, like a third of you, a quarter. Great, fantastic. All right, so for those of you less familiar with the topic, it's very, very simple. The typical machines people dealing with are like milling machines, 3D printers, and laser cutters. These are the most accessible. And their working principle is insanely simple. You essentially take either a drill or a glue gun or a cutting laser, and you mount it to an XYZ table, right? So you have some sort of a little robotic arm that can move like a little plastic extruder, like a little glue gun. You move this around in some sort of pattern, and that builds up a 3D model. So it's a very, very simple, it's a very, like here it says, speak slowly. All right. Oh gosh, I tried so many times. Okay, I'll keep looking at that. All right, so the machinery is very simple. It's a little robot that moves something around in space, removes some material or adds. So, and actually in many ways, you can make one yourself. There are many systems online that you can replicate. Now, the reason why I'm personally super excited about this topic is because it makes mechanical engineering tractable to computer science, and I personally have a hinge for mechanical engineering. So if you think of a traditional workflow involving mechanical components, it was you had a mechanical problem, and you created a mechanical solution. So here's an example for that. Here's someone who makes a key, right? So you have a very specialized machine. You take the key that you want to copy, you put it into the machine, and then you have a blank key. It looks the same, but it's missing the pattern. You stick it in the machine as well. And this is a copy machine. It's a milling machine on the left side and some sort of a scanning thing on the right side. And the machine scans the right key and embosses that directly into the key on the left. And I'm sure you carry many keys in your pockets that were made that way. Now, this is kind of the traditional workflow, and it involves a highly specialized machine. Now, if you think about modern workflow works with personal fabrication machines, it's slightly different. You have a mechanical problem, you end up with a mechanical solution, but in between you scan the object, or in some sort of digitize it. In some cases it would just be scanning, and at the end you print it. But in between now you have a computer science problem, or at least a computer science formulation of a mechanical problem. So for example, if I wanted to duplicate this cup here, at the end, I'm going to have duplicated cups the same way as I have duplicated keys. But in between, I'm using different machines. I'm using a 3D scanner, and I'm using so you could say, well, what's the big difference? The big difference is the thing in the middle. Now, for a brief moment, we're actually producing a digital object, and that is the whole thing. That's what this is all about, because now this is in computer science land, right? So once something has been digitized, computer science will come with this full force and come at the problem. So, and the key of this kind of digital cup is the fact that it enables a new workflow. So here's an example. In the car industry, for example, legacy parts are a big problem. So if you're a proud owner of a 1974 VW Golf, and let's imagine the bumper cup here breaks. So this part kind of breaks here, and you just want to replace that part. Now VW has a library of old parts from all the different models over all the different decades, and they're all a little different. And they don't like this very much. It's a very expensive operation. They hardly ever need it. And when they're going to sell it to you, it's going to be tremendously expensive. It's going to come from in the world. It's going to take 2 weeks to get to you, and you're going to pay an arm and a leg to buy this piece. So with 3D printing, this process changes. What you do instead is you just hold a digital model. You produce it on demand. And if you think about it, ideally, it's not even fabricated there. Ideally, it's fabricated in a 3D print shop close to you, or in some distant future, it may be produced at your home as well. So the moment you realize this part is broken, you contact VW, they send you the part, and you fabricate it on your machine, and you continue mounting it the same day. Now, if you think about this, that is a digital workflow. That's not the classic traditional mechanical workflow anymore. That's essentially a database solution to a problem. It's a computer solution. Only the very last bit is a fabrication machine. So there's tremendous promise in this. And I think that kind of shows the potential of this thing. On my personal level, the reason why I'm excited about this is because I'm a computer scientist, and I think my whole life I felt I was kind of enclosed in a little box, in the box of data. So every time I would do data in, data out, I'm kind of liberated by these fabrication techniques because they give me a chance to interact with the physical world. Okay, so let's look at fab. So who's driving this today? So on the one hand, we have companies like Stratasys, but there's another force at work here. So this is a website, 3ders.org, and they show you 3D printer models. Okay, presentation's getting long. So there's a tremendous maker community who all enjoy making things. Only a very small number of them for commercial benefit. They're very excited about the topic itself. And that has a tremendous impact so far. And what's amazing about especially 3D printing and laser cutting is that many of these machines actually apply to themselves. So if you think about the early beginnings of computing, the first thing that a system would have to do is a compiler would have to compile itself. And so here are machines that fabricate themselves. And that's a tremendously interesting thing because it also means that people are interested in fabrication instantly start contributing to the field of fabrication. So this is a community that actually generates more and more knowledge in all these different models. It's really fantastic, really amazing. The install base of 3D printing is small today, but there's certainly an exponential growth. And because it's so early, most of the systems we see today are still kind of geared at makers. So for example, there's a research prototype from people at Microsoft Research in Cambridge called Enclose. And it allows you to kind of fabricate or build a system based on Gadgeteer, but then there's also directly a system that allows you to fabricate the enclosure and all the mounts and bosses you need to assemble the whole thing in one process. You can kind of make not only the electronics in there, but also kind of generate all the enclosures with it. At the same time, I think Kickstarter is kind of certainly a revolution. If you think about it, if you kind of, a few of you who are my age, I think the dot-com bubble was a big thing. Then everyone wanted to write. And today, if you're a student yourself or you have students, Kickstarter is something that's just the way how kind of the startup kind of craze right now. And you will see that most of these projects have some sort of personal fabrication systems. There's a small number of user-facing systems that have come out over the years. Here's one called Sketch Chair, and it's a system that allows people to kind of make custom chairs on the web, like the 2 chairs these guys are sitting on, and you can go to the website and actually instantly test the whole system. So right now, but the question is, where should this whole field be going? Because that's kind of the mission of this talk here. So if you look at the evolution right now, this is the first machine that I bought from my lab, and it was 6 million yens. It was a machine I bought from Stratasys, a Dimension Elite. The next one I bought, and this certainly was targeted not at me, but at industry, right? So people who kind of company like Oxo, so who make like grips, like, you know, maybe Logitech when they designed this thing here. The next thing I bought was a MakerBot. It cost only 6% of the previous one. So instead of having one machine, I didn't do that, but I could have just populated a whole lab only with 3D printers. Insane. Every one of my students could have had 2 3D printers now. I thought this was crazy, and now everything was done. And then the last one I made was a PrinterBot. And it was $300, so it dropped by another factor of 10. So at this point, the price of a 3D printer is essentially the one as for a cheap netbook, okay? So that raises the interesting question, if this was for industry and this was for makers, this certainly is not a consumer device, but could we reach the price point at which this could become like a mass product somehow? Is it possible that 3D printing and fabrication could become a mass market, and meaning that everyone in their homes could have one, and what would that mean for the world? There's some websites that seem to support that. So for example, Thingiverse has over 100,000 3D models. So if you didn't know anything about fabrication, you could just go there and download, the same way you download something from iTunes, like a piece of music, you can download a 3D model and fabricate. And then, you know, we're not always making the smartest things with it. So at this stage, actually, I think the actual consumers, many of them who have one and they show you what they printed this. So, I don't know. So this is an interesting point in history because it means, like, what is going to happen? So it certainly has happened in industry, but what are the next stages? Here are 3 possible futures. So when we meet again in like 20 years, maybe it's still going to be a maker thing. Some of us will do it, we're going to tinker around. Version number 2, maybe everyone at home has a 3D printer, but they're not doing anything interesting with it. They're just downloading things and they're consuming, kind of like an iPad, you know. Well, iPad has changed a little bit, but in the beginning, people would just watch videos on it, and so you just consume, but you're not producing anything. 2 possible futures, but I'm mostly excited about a 3rd possible future in which consumers actually become active contributors and in which we kind of collaboratively solve hard problems. So to kind of show you what I mean, let me go back in history to what I think of as a critical moment in the evolution of CS and certainly HCI. So you've seen this face before. This is Doug Engelbart, and in 1968, he gave a very influential demo called the mother of all demos, and he said, he's wondering if you as an intellectual worker had a computer system that was instantly responsive and that was accessible to you 24 hours a day, what value could you derive from that? And as we know, I mean, this kind of resulted in tremendous change with, you know, the same work being picked up by Xerox PARC, building the Alto and the Star, and essentially became, you know, the machine that is on in everyone's home and office today. So Doug Engelbart had a great vision. I don't know if the world ever fully understood it. And he certainly seemed frustrated about it, but I think he actually succeeded. He talked about augmenting human intellect. So I actually don't think it, in some ways, the idea, if you go further back to 1945, Vannevar Bush talked about the MEMX, the idea of a memory extender, a machine that helps you think better. And I think the PC really succeeded at these things. It certainly also did a lot of things to distract us, where we're kind of wasting our brains rather than becoming smarter. But if you think a lot of things like video editing, desktop publishing, the whole wave of things, the internet itself, all these things that became possible because it's been a tremendous augmentation and a tremendous boost to the public IQ. So a lot of hard problems were solved because people have these thinking machines that help us think better. How good would you be at math if you didn't use MATLAB? How good would you be at layout if you didn't use InDesign or so? So the pattern that we see today that's ready for us waiting in 3D printing is the same pattern we've seen in the past. It's a mechanism of digitizing the necessary ingredients. Then there can be a computer system that adds some smartness to it and a machine that executes at the end. That's a standard pattern we've seen repeatedly in computer science, and it's tremendously powerful, and it all comes down to adding smarts here. So if we can build good systems that help people do things they were not able to do before, and I show you a lot of these examples today, then we're actually onto something here. So I think the grand challenge that we should try to think of is I would like to see personal fabrication tools kind of along those lines of Doug Engelbart's vision of augmenting human intellect, and just think of them as tools that help us not just think better, but also construct and interact with the physical world in a better way. If we get a couple of extra 100 million people on the problem, maybe we can create better motors, better environmental consciousness, space elevators, whatever we want. More problems can be solved if more people are looking at them. So in order to get this started, a lot of good research is necessary. And this is actually, so my student Stephanie just compiled this chart for me last night. This is actually very interesting to see. So if you look at the mainstream ACM conferences on interactive topics, you see there was essentially nothing before 2011. And there was one paper at SIGGRAPH, and then there's been some sort of a trend since, right? And obviously, it depends on what you declare as personal fabrication. There's a paper from 1996 by François Guérin, actually is a predecessor of personal fabrication. Now, the interesting thing is the Chi conference in 6 weeks now has 15 papers on personal fabrication, so there's multiple sessions and tremendous growth. So if you're looking for an interesting new topic, let me advertise this. I think this is a great topic. Think about it. Right, so let's get started. So here I think the 5 kind of sub-challenges that we have to solve in order to make this a successful thing. So let me start in the middle. I think the main reason why I'm giving this talk to you guys, because I think that interaction is the key challenge here. When you had this model with a cup in the middle, adding the smarts is the key thing. And a computer system is not interesting unless it can augment you and can help you do something otherwise would not be able to do. So the main challenge is in the user interface domain, adding the smarts. But to get started, we need to have good hardware, and we need to have interactive rates as well, right? Because many interesting systems are not interesting until they get fast enough. And I'll tell you later, we're essentially still living in the days of batch systems, where it's very slow. We say, okay, print something, we go drink a cup of coffee, or we just leave for the day and then we go back. So there's not a lot of cool HCI systems kind of work on this kind of model. And then when I'm done with the interaction things, I'm going to take a quick peek at the consequences on the society level. One of them is sustainability, and the other is intellectual property. And I'm not going to take these topics all too serious for the time being right now. But there's still something that I think we need to start thinking about. All right. And I hope you believe me that all of these will be influenced heavily by interactive things. So you are exactly the people who should be working on this. You have exactly the skill set to kind of do these things. All right. Let me start talking about materials. All right. So if you look around, the machines you can buy today, if you just look at 3D printers, they actually have resolutions up to 1600 dpi. I don't know if that's an interesting number, but it means that's kind of is the resolution that traditional printed pages are made on. Many laser printers have only 600 dpi, so 1600 is a very, very high number, a very, very fine detail. In addition, some printers have volumetric color. So it's not just that these things are fully colored. If you break them in half, you also have color in the middle. Okay, not sure why you need that, but it's cool. So in some ways, you could say we could stop right now because we've already reached the resolution of eye. So that's when we stopped 2D print, when we were able to make things that looked perfect to the human eye. So we could stop right now if we were only interested in decorative things. So as long as we're only making things that we're putting on the shelf and looking at, we're done at this point. But I think we should not just be looking at decorative stuff. We should look at how to help people solve hard engineering problems. And it turns out we need more for this. So in general, shape is not quite enough. We need to talk about other things. So one thing we can throw in is materials. So let me actually start with a somewhat decorative example, which I still like a lot. This is work by Scott Hudson shown at the last Chi conference. And since I have a little daughter myself, Philippa, this is so insanely endearing too. I thought this was a great example of, My daughter was initially planning to travel with us, but we have a measles outbreak in Berlin, so right now she couldn't travel. I'm very sad. I would have liked to introduce it to her. All right, here's more materials that I think are very interesting. Here's one, clear materials. And a couple of researchers, including Carl Willis and other people at Disney Research, a while ago showed how to make interesting interactive components with them by using light pipes. So in all of these systems, there's an LED and a light sensor and 2 different ends. And then a clear plastic piece transmits the lights, and depending on how you shake it and push and so on and touch, you can actually recognize these things. So now you can make use of a 3D printer to build something that actually has a UI component built in, which is very interesting. And it's not a mechanical one, it's actually an optical one. A huge topic over the past couple of years is printing conductive materials. Now, the vision is you want to make a 3D print and not just have the 3D print and then start putting your components in. Ideally, you want to print the conductive paths in the PCBs directly into the 3D model, maybe combined with a pick-and-place machine where you take like electric components and mount them into the object. So when you're done fabricating, you already have a working system in one piece. Jennifer Lewis Lab made good progress on this topic recently. So they actually created some wonderful, so the resistance is the main topic here. Some of this material exists, but the resistance is too high. It doesn't quite work it. They made this really cool stuff, and this is a wonderful prototype here of a new data glove. Little strips of the stretchable material on it, and as users flex their fingers, the material is stretched, and the resistance changes so they can measure the position and the posture of your hand using this very thin glove. All fabricated with a 3D printer. One of the recent breakthroughs, just a couple of months ago, this came out. Someone printed a 3D, using a 3D print in LED. So you can think about the next thing, maybe you're not going to have just the wiring on it, maybe you're going to produce light-emitting diodes on the actual thing. So materials certainly are a big area, and a lot of materials are happening right now. And I think we'll do more with metamaterials. So if you think about it, there's more than that. There's not just the material, and there's not just the overall shape of objects. Some objects just have interesting internal structure. So the metamaterial level is kind of under research right now. I think we need more research on this, and it sticks between these two levels. So a metamaterial is essentially something that is determined by the arrangement of the material rather than the material itself. So let me show you an example. This takes a little bit time. So this is actually, these are all round holes, and you can see some of these holes are like pushed flat and others are pushed spiky. And now we're pushing from the top, and you can see how like this actually pops in a second here and changes its orientation. Can you see that? And it's like, blop. And then there's a point at which the whole kind of thing rearranges itself. So 3D printers are fantastic at making things like that because they're good at, let me show the video again. So the left chart actually how much force the thing actually exceeds right now. So it's pushing, 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 pushing. Now it kind of breaks in. All these things kind of rearrange and assume a different structure. So you can actually, using these microscopic arrangements, you can create material properties that are outside what natural materials would give you. So you can't go to a store and buy wood or anything like that that behaves this way. Here's some structure, an audio filter consisting of very, very small microscopic structures that filter audio in a very, very different way. So this is a fantastic topic for 3D printing because 3D printers have millions of degrees of freedom that are unused today. If you look at Thingiverse, in many cases, 3D printers just produce like a box somehow. What a waste, right? What a waste. The same 3D printer in the same time could arrange the material in some insanely complicated pattern. We just don't. At this time, we always seem to care about is the outside of the object. We're caring about the inside of the object and get very interesting properties out. So at this point, which is important, that actually will demand printer resolutions. When I said in the beginning, 1600 dpi is what we have right now, I think in the future we want 16,000 dpi or whatever. At some point, we want molecular control. We want to be able to arrange the atoms, and molecules in the system. So today we're at the stage where all we care about primarily is shape. We're just getting into a point where we start caring about materials, how things feel, some electric properties. And I think in the future, we're going to care about the internal structure of 3D print, and we're going to need a lot of resolution for doing these things. And then ultimately, I think, if you think 50 or 100 years out, the machines we're going to be using will have insane resolution, and we'll be able to produce fantastic objects. All right, so much about materials. Let's talk about speed. And speed is actually getting much more HCI. And all right, let's check it out. So here's my 4 words of German. Alles schläft, einer schafft. Everyone's asleep, only one is working. So this is from AlphaCam, who sells Stratasys machine in Germany. And they think of this as an advertising. I think it just says our machines are really, really slow. Well, you already go home. Our machines still have to keep working because they're so insanely slow. And now, obviously, this is not a problem of this company. I don't want to poke fun of them. But that's just a problem for the whole industry right now, right? Fabrication machines are very, very slow. If we want to make something small, it's going to take an hour. If it's larger, it could take a day. And if you're going to fabricate something larger, it can take weeks, actually. So we seem cool waiting for this. But then I'm sure we were also cool waiting in the 50s, waiting for a batch job coming back from a computer. Right? You would have computing in the 50s was you had a stack of punch cards and you put them into a computer and you came back the next day and it said error in line 15. So that's kind of where we are right now with 3D printing. You print something, you're like, oh no, it doesn't work. Let me print this again. So we were happy until we figured out, until people like Doug Engelbart and Ivan Sutherland proposed that we can actually do these things interactively, and that changed a lot of things, obviously. So in our lab, we've looked at a couple of these things, and one of them. And the idea of low fab is, and the sample I showed you earlier belongs to this to this area. So we had this idea to make low quality prints that would be very, very fast. And it was not clear what to do with them somehow. Initially, we felt like, well, we could just make an object that's very fast, but it's going to look very little like the original object, so maybe that's not what you want. So we could be 10 times faster. We could do something in the minute range that would take hours before, but it was not clear what to do with it. But what's interesting is it actually has a meaning in the context of a workflow. So if you're a designer, let's imagine you're creating a product, and the same holds for designing user interfaces. You don't start with a high fidelity interface. You start with something that's low quality. And if you're making in between prototypes, maybe there's no necessity. Today you print high quality, oh, it's not right. You print high quality again, you print high quality again. And we think like maybe in the future you want to have a 3D model, you want to print low fidelity, you fix all the problems. At the very end, you print high fidelity. And maybe that last print prints overnight, but all these other prints print within the day. And rather than dragging out your 3D design over a period of a week, you're going to do it the whole thing in one day, print the final thing overnight, and ship it to the customer the next morning. So here's the first thing we did called Fabricator. Our first idea was we're going to use Legos for this. It's a really funny system. So here's a head-mounted display. And let's imagine in this first round, I'm only interested in the optical properties. I just want to get the lenses to the right location. So these lens holders, they are actually 3D printed, but everything else is Lego. So this is what the system looks like. You load your 3D model. This is the 3D model. You say Legofy, and it makes Legos out of it. And now we say, like, we're interested in the lenses. So now I'm going to go in and going to mark up these lens holders as 3D print, and the other one as well. And I'm adding little flanges to them, like here, so it actually connects to my Lego system. And now I'm saying export the STL file. I'm sending this off to my printer, and it's only going to print the little part that contains the lenses. And as this is printing, I'm actually assembling the Lego bricks according to instructions on the screen. And when I'm done assembling the Lego bricks, the 3D printer is ready to, and I kind of make this thing. The benefit of this approach is I now have a prototype that I can actually try out very, very quickly. And this actually fabricates about 13 times faster than the original version. And now I say, actually, I'm unhappy with other pieces. And the modular system allows me to swap out more components. And now I'm actually fabricating other parts of it. If you're interested in this, we're developing a public version of this right now at lowfab.net. So send me emails. We're very excited if you're interested. It's cool for teaching as well if you have very little class time and want to quickly print something. I love this thing. All right. So the second prototype was called Wireprint. Fabricator was not very good at maintaining the shape. If I wanted to test the ergonomic fit of something, the Lego thing just didn't quite do it. If I the model really fits my hand, Legos were not right for that. So we made this version called Wireprint. And what's interesting about Wireprint is that we reprogrammed how the 3D printer actually works. So traditionally, the 3D printer, as you see here, only prints layer by layer. And we kind of made a software solution that actually changed the 3D printer to not just go layer by layer, but to actually move up and down and do a vectorial model where it holds the material mid-air, waits for it to solidify, and just kind of performs this kind of delicate little dance without the material collapsing in place. And so the benefit, again, is we get, depending on the model, we get a speed up of 5 to 20. And we can make things quickly. So you could check, does this handle really fit my hand? No, it's a little too big, should be a little different. You check it out, and then you reprint really quickly. And then the last in the series, we're going to show at the Chi conference in 6 weeks. It's called Plaitner, and it's a conversion from a 3D model to laser cutter. So Plaitner actually kind of takes the 3D model and extracts everything that looks like it could be laser cut. You can choose how much of conversion you want, and it converts round surfaces as well. So it actually does a decent job at getting you a good amount out. So it's highly customizable depending on what materials you want. So you can have models that still have 3D prints in it, or they're completely converted, and again getting the speed down by like factors of up to 50. All right, so that's the idea of low fab. Taking fabrication that would normally take something like an hour or so and getting this into the minute range. So we pushed further on this topic, and we were wondering about if we can get the interactive rate even further up. And so how can we interact in seconds? So if you think about this in computing, today we're still working in batch world. So can we do something like a command line? You type something in, you get something back. You type something in, you get something back. And so we made a system called Constructible, and the person in the video here is actually my student Stephanie, who was first author in this and other papers. And the idea of Constructible is that you use a laser pointer to work directly on the workpiece. So I don't know if you can see the red laser dot here. As Stephanie is painting, drawing around on the thing, there's an overhead camera that observes the dot as it moves around. And then it's beautified and instantly fabricated. So you can work with this thing a bit as if it was a touch screen. So you have different tools. You have one tool that only does polylines. One tool only does extrusions. You can trace physical objects. And it does some higher level structures like finger joints, for example. You can say connect this to this thing, and it actually makes the matching finger joints and makes gears as well. So the example we showed at the time was we showed how to make this gearbox here interactively. We've taken this on the road. We've shown this at Kai. When Kai was in Paris, this was reasonably close from Hasse-Plattner Institute in Berlin, so we actually drove a laser cutter there. And we made kind of things like this little booklet with people. So I like Constructible a lot. I think the concept itself is very promising. It only made two-dimensional things, though. And so we made another version of this. We call it laser origami. I don't know if I'm pronouncing this properly. And the idea here was that we wanted to bend the material as well. So this is what you notice here. The plastic is not on the ground. It's actually propped up a little bit. And now I'm moving the material away from the laser. As a result, the laser gets defocused and doesn't heat up anymore. It's not hot enough anymore. So as the laser moves back and forth, the material will actually just melt there. It's not going to burn. It's going to melt. And so you can see how you can bend a piece of material. So this is a little holder for a camera for an iPhone. So you can stick it fabricated in one process. So it comes straight out of the cutter, no need to assemble anything. So 3D print would be 4 hours, and in 3 minutes you can have a laser origami version of that. Let me show you one more because it's kind of fun to look at. Here's another example with a holder. So as the laser heats it up, you see how the material kind of becomes soft and sinks away. And it's kind of fun to watch. So now it moves again to the laser. Now the laser can cut again. We can cut out the object. And because we're computer scientists, Stephanie is actually going to use some flat cable to mount her planting pot here. There you go. All right. And thank you so much for the book on origami. And we're sure we're going to use that in the next version of it to improved version, better folding. Thank you so much. All right. There's a lot of work in this area. If you think this is interesting, a good work also published at Kai and SIGGRAPH, such as the 3D system from the Media Lab. All right. So this got us up to an interactive rate of a second. So we built one last prototype where we tried to push it as far as we could. And the idea was to interact on the per feature basis, and maybe we could have some real-time interaction. And this, we haven't published this one yet. So batch system command line. So now we're trying what could direct manipulation be like on a system like this. And think of this as more of an art project. This does not do anything productive for that matter. So it's a game, two people playing. You put like in the shape of a €5 bill in, so does the other person into the laser cutter. And then what you're going to do is you're going to shake an iPhone as hard as you can to drive the laser into the dollar bill of the other person. Okay? All right. I have to shark really hard and drive the laser over to the other side. And this is what it looks like. Oops, shit. Sorry. I shouldn't swear on stage either. PowerPoint, help me. There you go. Okay. It drives the laser over to the other side. And if you're playing this really well, then I just love the look on Ji-Yoon's face. I think he didn't realize that. Anyways, all right, don't do this at home. So that's how we try to explore like interactive rates with the laser cutter. And the trick here is that what you're doing right away is transferred to the laser. We use the Chinese laser source board to get direct access to the board to implement this real-time interaction. So what if machines actually get faster? What I showed you how to do faster things, but in reality there was a second axis, unit size of the interaction. So if you want to make a complete model, it was still slow. I just said we can go faster if we actually interact on smaller grains. So everything on the left is possible today. In the future, machines will actually get faster, and the question is, what is the future going to bring? So I think in the future, when we can print really quickly, we will do to animate. All right? So, I mean, I'm talking 100 years out. If you have a really fast machine, You know, the machine should be able, you could just say, oh, I'm going to print 50 models in a second, but maybe you want to give one model and that gets modified really, really quickly. I don't know what the technology is going to be. But when you look at sci-fi movies, when people interact in VR, it would be nice if that was a physical model, right? If you can make it really big, maybe you can live in it. It turns out this dream is not, you know, this has been around for a while and other people have thought about this. So for example, here's a video from Hiroshi Ishii's group. And I'm sure many of you have seen this, the inform shape display, and there's many other shape displays as well. The main idea is that you're having something that changes shape in real time and actually gives you the affordance of many different objects and systems out of having only one that does everything. The same dream has been dreamt by people in modular robotics. You have one robot, it changes shape and adapts to what you need to do. Today, the same thing is called. The idea is to use a good number of those, maybe 100, maybe 1,000, maybe more, that self-assemble into some shape. Now, it turns out, you know, they're all having the same dream. So here is an envisionment video by one of the smart matter companies. This is kind of the envisionment that one object that you can manipulate like that. I'm not sure that smart matter is going to accomplish that, though, because smart matter has a lot of interesting questions. This actually looks much more like a 3D print, right? So if you envision if 3D printing was insanely fast, you know, what could this look like? So the idea of every single component needs to be smart, has its own microcontroller, its own battery, and so on. Maybe this is better accomplished by, you know, some sort of a robot that has a print head on it and can print to itself. And if it needs something, it just extends itself and makes something. Anyways, I don't know how to do this. I'm just here to ask the questions. But if you have any ideas, please talk to me after the talk. I think this is an interesting challenge. Maybe you guys can help solve it. All right, so that was discussion about speed and interactivity. So let's look at the interaction level of how to get smarts into a system. So the main idea was we wanted to have a system that adds smarts here. So the system takes care of the mechanical parts, and the user is just trying to do something interesting, and the system is going to provide some of that expert knowledge. So a lot of the systems today are just dealing with shape. I think they're not the most interesting ones, but there's a good number of systems now that deal with kinematic, static, or even dynamic interactions. These examples. Here's a system, and this is all done that happens, work done happens in the context of SIGGRAPH. So the system actually did a static analysis and realized that these legs are not very stable. And so now the user goes in and actually reinforces this leg to then refabricate it and get a stable model out. The general idea of these systems is that users are not very good at dealing with forces, but they're very good at dealing with shapes. So the system takes care of all the forces, and the user deals with it in the form of shapes. Here's some kinematic systems. I really like this one here called Chakra. So the user draws a model of a backhoe. And now he can pose that model. So he or she will now say like, well, if the backhoe is in the up position, these parts will be here. And then at that moment, the system creates actually the structure to operate this thing. So now you have a crank here that you can turn, and when you turn the crank, you actually have created the system. Now this is a system that makes something that's hard easy, because normally users would not have been able to produce that, but now you have a system that actually produces this, this kind of interesting backhoe for you. Other researchers at Disney Research have looked at how to create running, you know, kinematic models of like. Again, this is something that a normal user would not be able to produce, but with the help of a system that becomes possible. So a lot of this comes from researchers in computer graphics. And here's another very interesting model from actually Takeo. He's in the audience here. So, which is one that I really like, because people are very bad at making model airplanes. What's interesting about this model is it allows people to kind of design and sketch what they want it to look like, and then they say make it fly. And now the system actually provides expert knowledge and what makes a plane fly. And you can move things around until you get like a good trajectory out. And then you can say, okay, well, this actually flies. I just love the fact that there's also good, wow. Okay. So what I like about these systems is exactly what they should be doing. They take a hard problem. They use fabrication machinery to digitize a problem and to fabricate a problem, and in between they provide some smarts that allows an inexperienced person to solve a hard problem. I think there's lots of problems open there. As we scale up 3D print, I think there will be more interesting challenges. I would be very interested in someone who can make a system that designs running stilts. Why is that an interesting problem? Well, it's a dynamic problem. Energy, it has to have the right tension. Like my stilts are different from your stilts and from your stilts because they take my body weight into account and so on, right? So I think there's a large space of things where like your expertise could be used in making these systems. Now, we don't necessarily know a lot about mechanical engineering. What we're doing as a group right now is we're learning all these things about mechanical engineering so we can implant it into these systems. All right, so much about the interaction level. So let me talk briefly about societal impact. So let's imagine everything works out and these systems become really, really big. Lots of people have them in their homes. What are going to be the consequences? The first issue we're going to have is a sustainability issue. So by the way, that's a super open topic. If anyone has ideas, if you're looking for a topic, if you have good ideas, sustainability is like privacy, always something we think about afterwards. But we should think about this early on this time. So I couldn't find the page, but a couple of years ago, there was a wonderful artist who made, just as an art piece, he made a system that fabricated plasticware for him to eat on the fly, and then he would throw it away. He would eat and throw it away, throw it away, throw it away, all the time. It was a great art piece because it points out the difficulty, right? The pain point is if we fabricate, we're going to produce trash. And I think these are things we're thinking about. So the field has started to look at recycling of filament. These multi-material printers will be very hard to recycle. Metamaterials are made from a single material, so they can be easier to recycle. These are all things that will matter in the future. We're doing a little project right now called incremental printing, where the idea is that we're not going to reprint every single time. We're just going to take an existing model and just going to reprint the part that is modified. So here's a model. We have a milling machine in the, we installed a milling machine inside of the 3D printer. We can mill and fabricate in the same printer. So here's a 3D model we made, and we had two versions of the head. This was the first one here. Then we didn't like this, and we changed to that model. So maybe that's an interesting idea how to move forward, just to print less. All right, I think the harder issue ultimately is not going to be the 3D printing material. I think 3D printing is going to go through more evolution. Every 18 months, or whatever the number is, you're going to have a machine that will be faster, have more resolution, use more materials, be nicer in some ways, and you're going to throw out your old machine. The same way, this is just trash from computers, right? Computing actually is a tremendous amount of trash. The biggest trash actually comes from these things here, right? We've never thrown away things so quickly as we're throwing away mobile phones that produce a lot of trash. And I think everything that has a fast evolution will produce a lot of trash. So if you have any ideas, these are relevant questions. How are we going to prevent people from actually throwing away stuff every 18 months? All right, so quick hint on sustainability. And the last thing I want to talk about was intellectual property. And again, I don't take this topic too seriously, so here's our take on this. So my aunt is 83, and a couple of months ago, she asked me, what is digital? It was difficult to explain. I failed miserably, I have to say. I actually went home and I read Wikipedia for the rest of the day. But I think the true answer of digital is this. Digital is something that allows you lossless reproduction, right? In analog, every time you touch a signal, it gets worse. In digital, every time you touch a signal, nothing happens. You can copy as many times, you can modify as often as you want, the signal doesn't change. And so whenever we look at this workflow, it's not just one. This virtual thing here becomes many. So if you have one object, you instantly have a million. Stick this into BitTorrent, you have a million of it. Okay? The same will happen in 3D printing. It's not like this digital cup is not just one cup. That instantly is a million cups. And so what we're going to run into is we're going to run into the same thing. Designed once, shared a million times. So for example, if you design a clever iPad stand like this one here and you're selling it online for 10 bucks, maybe it takes only $3 to design it, then you have $7 that are your design, and they're in this thing. So traditionally, the thing and the right to own it were the same thing, but the same as for media. It used to be, if you owned a record, you owned the music, and if you didn't have the record, you didn't have the music. But today it's different, right? You can own a lot of music. Well, you can possess a lot of music without owning it. So it's interesting. I don't have a particular opinion. I just don't like how it goes right now. So this is what happens in Germany right now. Lawyers sent you letters that say, like, please stop downloading MP3s and please pay $1 million. So I think there's a good chance that that's going to happen in 3D models as well, where you're printing something and someone says, this looks very much like, look, my design did this in 1964. Please pay me like $30 for this thing. Authenticize.com actually goes the same direction as music. They're starting to stream G-code, so you're not downloading the 3D model anymore, they're streaming it, so ideally you couldn't intercept it and store it. And here's a personal perspective on that, so don't take this one too serious. This is more of an art project. So we looked around for teleportation, and it turned out there's two types of teleportation. Either you have a wormhole, right? If you want to get from A to B, it's like whoop, you go in here and you come out there. Or the other direction, more used in Star Trek, is here, and we refabricate you here, okay? So we thought, like, maybe we can make this today. So here's a system, in homage to, you know, a TV show from the 60s, we called this Scotty. Is that called Scotty as well in Japan? Scotty, beam me up, like in Star Trek. Ooh, okay. All right, so you pick out, you want to send it to Julia, and you say teleport. And now what the system does, it uses a built-in milling machine. It grinds down a layer of the object, takes a photograph, grinds down another layer, it takes a photograph. So it grinds down the object. The thing about this process, it makes sure that exactly one object is being reproduced. The original is destroyed. It was encrypted. It can only be decrypted on the receiver side. So this is a little necklace pendant that for his girlfriend Julia. It's a little snail model. And as it comes out of the 3D printer, it's the only one there. We know the system guarantees there's only one of them. And so one of the potential uses for this thing, we thought about many personal uses, but you could think about using this on eBay. If you're buying something from someone, maybe in the future, you don't just buy an online auction on eBay right away. You buy it right away, you pay for it right away, and today then you wait for 2 weeks for the object to show up. In the future, I think maybe the other person's just going to put into some teleportation thing and going to show it to you right away. All right, so that's a kind of tongue-in-cheek discussion of intellectual property. All right, so these were the 5 points I want to make. I hope you agree with me that HCI is like a driving force behind these things. If you can make an interactive system, that is the key component. And I'm super glad to see that a lot of good work is coming out of Toronto here, at this very location where we are right now. So what's going to happen in the future? So let me look at the PC to fab analogy one more time. So the same way, I think, here's my prediction what's going to happen. Every 18 months, PCs double in storage or clock speed. And the same is going to happen for printers. Every 18 months, they're going to double in resolution or speed. Okay? And that's actually happened. So this is the 3D printer that creates one layer at a time using a DLP projector. It produces one layer at a time. The same way that compilers compile compilers, fab machines will keep making fab machines. So if you ever believe in the singularity, the day when human intelligence is superseded by machines and machines start making machines, this is kind of as close as we're getting right now. We'll be able to pack unimaginable complexity into objects. This is just a make-believe model of an iPhone, but who knows what we're going to be able to produce in the future. So it's going to be very promising. We still live in the days of punch cards right now, but we're going to be living in command line interfaces soon, and I hope we're going to make it to direct manipulation. I hope we're going to get to systems where we can actually, interact and mold, kind of like Iron Man creates in prototypes, in actual physical matter. I think that the prototyping techniques will become more like the prototyping techniques, again, that we use from PCs. And I think the whole attention will go where, if you think about personal computing, like 30 years ago, was all about having the fastest PC. Then it became about software. Then it became about training. And today it's about maintenance. And so that's kind of, I think, the same trajectory we're going to see with 3D printers. We're going to sue each other. Hopefully not. If you find a solution for that, I would be utterly grateful. I don't like us suing each other. I think that's a very bad thing to happen. And there will be new startups. Maybe your startup. Maybe you're going to be the next Apple. All right. I think HCI teams will change a little bit. We're not just going to have designers, computer scientists, designers, psychologists. We're going to have more kind of people with a traditional engineering degree with us to work on these topics. And my personal hope is that fab will become a tool for exactly along the lines of what Dr. Engelbart was saying, as a tool for human augmentation that helps us kind of make better decisions, solve bigger problems, and boosting kind of the public IQ. Here's my first request for a space elevator. All right. So maybe when you think of Vannevar Bush's idea of the Memex as being that tool that has like 2 screens and you solve hard problems on it, maybe the Memex, that's what it's going to look like. All right. I would like to thank my students, foremost Stephanie Müller in the top left. And with that, I'll be happy to take questions. Thank you so much.